This podcast is sponsored by the new edition of the Bible for testing homes, Home Performance Diagnostics, the guide to advanced testing, with the latest tools and techniques that prove you're worth the extra money. More at homeperformancebook.com. Enjoy.
Welcome to the Building Performance Podcast from Green Dream Group in Chicago. I'm John Bergman, filling in for Corbett Lunsford, and today we're talking about the EPA's new guide for moisture control in buildings with Lou Harriman and Terry Brennan. Lou Harriman is the Director of Research at Mason Grant Consulting in New Hampshire, and he spent 40 years solving moisture and humidity problems in buildings. He's written and co-authored tons of books, including ASHRAE's Humidity Control Design Guide, Measured Home Performance, and Reducing Source Energy in Commercial Buildings. Terry Brennan started out as a physicist and has been crawling around in attics and basements for about 40 years now, contributing to research in radon and moisture control. And he's the lead author of the EPA's new publication called Moisture Control Guidance for Building Design, Construction, and Maintenance, which is available at the EPA's website, and we put a link here on this episode's page at buildingperformancepodcast.com. So Terry, let me kick this off with you. My first glance after reading this guide, it seems like this is not just for high performance or what you would call a green building, and it actually applies to any building in general, whether it be residential, commercial, or industrial buildings. Would you say that's pretty accurate?
Well, the physics and the biology don't change from building type to building type, but the methods, materials, and the design and construction process is quite different for commercial and institutional buildings than it is for most residential, certainly single-family residential.
I think that the rationale for this is pretty straightforward. The fact of the matter is that an awful lot of buildings, even in the commercial environment, have moisture problems. I mean, I think everyone who lives in a house is familiar with moisture problems at one point or another. They did a study back a number of years ago, the EPA did, of commercial buildings, and found that about 85% of the buildings that they surveyed in a random sample throughout the country, 85% of the office buildings had some form of water damage over their lifetime. And at the time of the survey, 45% of those buildings were currently having moisture problems. So the fact that so many buildings at some point in their life encounter moisture problems was a prime motivator for the EPA to create such a document. And it's not just because it's an unpleasant thing, it's also because there are health problems.
And who's the intended audience for this guide? Who ideally should be downloading and reading this?
Well, it's actually fairly broad. The document is divided up into 4 sections. The first section is a primer on moisture dynamics. The second section is aimed at the people who design commercial buildings. One is designed at the people who can actually construct the buildings. And one is aimed at the facilities people whose job is to keep the things working over the course of hopefully decades.
If I can add something, John, too, is that this is clearly a document that's designed for the professionals. At the same time, people that have problems in the building that they occupy are often really puzzled as to why they're happening and whether or not they should be concerned about it. And for those people that are interested in understanding the whys and the wherefores and what level of concern there should be, this is a terrific document for them. Terry pointed out that the first chapter is a primer in the whole matter of moisture in buildings and how it happens and where it happens and where the big problems are likely to be, and that's great. You know, I have several times referred building tenants, apartment tenants. Most recently, a friend of my daughter's in New York City who would very much like to know how come they're having these problems and where the problems are likely to be. And that first section is a perfect place to get a basic understanding of the problems of moisture in buildings for anybody.
Talk for a quick second about moisture transport. There are a couple different ways water can move in and out of a building, and we kind of want to suss these out and figure out which ones mean something and which ones aren't such a big deal.
I think, to summarize that, it's sort of the unholy trinity, right? You know, I mean, you got water that's coming in from outside, you got water that's dribbling in through pipes inside, and then you got humidity, and that comes typically from outside, although in swimming pools and other places you can have indoor humidity, or in low-cost housing you can have an awful lot of people generating water vapor, but typically it's Humidity is an outdoor air infiltration issue.
Great. And so when I was reading through this document, I thought it was great. Here in Chicago, typically we are dealing with mostly cold climate issues. However, especially when you get into the HVAC section, which we'll talk about here in a second, it's pretty clear that you guys harp pretty hard on the dew point, knowing where it is. So Lou, I'm going to defer this question to you. There's a section in here that gets pretty in depth about the differences between dew point and relative humidity. Now, without being too overly technical, why is it important to know what that dew point is and where it is?
Sure, that's one of the areas I think that I would like to really stress is that I think everyone is familiar with the concept of relative humidity because it's easily measured, and people talk about relative humidity, and people don't always talk or think about the dew point. But relative humidity is just relative to the temperature. So the dew point is an absolute measurement of humidity. Now, why would you care about that? Well, the dew point temperature is the temperature at which moisture is going to condense out of the air. So when the air falls down, gets low enough to reach its dew point temperature, then that's the point at which that water vapor is going to want to condense out on things. So we talked just briefly here about the importance of not having condensation inside. Well, if you know the relative humidity, you don't know much. But if you know the dew point, you do know the surface temperature that you have to watch out for where you're going to end up with condensation. So if you keep track of the dew point, and if you control the dew point, and make sure the dew point doesn't get too high, then you can be really conscious of how to prevent condensation. That's not true with relative humidity, because relative humidity changes with the air temperature. So that's not as useful in terms of preventing condensation.
So what you're saying essentially is relative humidity is a dynamic property associated with air, whereas dew point is less dynamic and is more set in stone. Is that correct?
No, that's not quite it. They're both dynamic properties of air, but if you focus on the dew point, you'll be less confused about when you're likely to be in a problem situation.
All righty. So what you're telling me is you walk around with a psychometric chart in your pocket.
Well, you could do that. I certainly do. I think all good, healthy people ought to have a thermohygrometer at their fingertips at all times, if not a psychometric chart, or maybe a couple of them. But no, it's not necessary to do that. There are thermohygrometers that you can get if you're interested in this subject. If you're concerned about condensation, you can purchase for not vast amounts of money a thermohygrometer that will tell you what the air dew point is, and that's a good thing to keep track of. If you're in the business of operating a building, it's a very good thing. And if you're in the business of operating a building, I'd submit that you probably have a budget for a couple $100 to buy an instrument that will tell you. And if you're a homeowner, if you have a budget for about $35, you can know what the dew point is without having to consult the psychotic chart, the psychometric chart.
I have never heard it called the psychotic chart, so that's great. So Terry, a couple times in this document, you guys actually give example of where condensation has and historically forms in buildings. Do you mind glossing over some pretty troublesome areas or some typical areas within buildings that you would actually run into that issue?
Some examples would be if you're in Gulf Coast states where outdoors is very humid and very warm with a high dew point almost all the time. The cold surfaces are air-conditioned portion of the building where all the surfaces are chilled by the air conditioner, and then the air conditioning surfaces themselves are cooler than that, down to if you have chilled water lines, maybe they're operating at 45 degrees or so, 42, 45 degrees. So there are some quite cool temperatures in there, and the outdoor dew points are like 70, 75 degrees F. So if any air leaks through the enclosure and comes in contact with any of the chilled surfaces, like the backside of vinyl wallpaper on the exterior wall, or a metal cabinet screwed to an exterior wall, or supply diffusers in the air conditioning system, or the chilled water lines where they run through demising walls, and there are air leaks that come in through the demising walls. And those are all common condensation sites for a hot, humid climate. In the north, the cold surfaces are in the wintertime, and they're on the outside of the insulation layer. So if you have warm, humid air from inside leaking out through the enclosure, you can expect condensation or frost on the backside of the sheathing or on the roof sheathing in a vented attic or on windows.
I'm going to toss over to Lou for a quick second. So you just talked about the enclosure. So historically with buildings, we haven't typically been building them very tight. Nowadays, many building codes are either enforcing through commissioning or they're doing some pretty intensive visual inspections for air tightness. So air leakage through the enclosure is clearly a problem. So how does HVAC and air leakage through the enclosure tie together, Lou?
Well, that's a great question, and they tie together very, very closely. I also want to defer to Terry on the subject of air tightness of buildings because he might be one of the dozen or so people in this country that knows how to really test large buildings for air leakage. He's been doing it. He and Mike Clarkin have been doing this for a lot of years for the Army, so they have a tremendous experience. And they also just finished a research project for ASHRAE, for our engineering society, on how to test the air tightness of large buildings. But that said, just to summarize it briefly, HVAC systems create pressures, and they create large pressures. If you think about air movement through buildings, it only happens when there's a pressure difference. So when there's an air pressure difference between indoors and outdoors, and there's always a pressure difference of some small amount, then that's the force that can move air into or out of a building. And that's the force that we want to, with the building enclosure, isolate. We want to stop the flow of air through the wall because, as Terry mentioned, in both cold and hot climates, we don't want that air flowing through the wall. We want an air barrier in there. We do want tight buildings, right? But we got to be careful about HVAC systems because where normal building pressures between indoors and outdoors are measured, I'll just give you a number, it's measured in pascals. It's a very small amount of pressure. Pressures between indoors and outdoors, differences might be anywhere from 5 to maybe 10 or 15 pascals in a low-rise building, very small pressures. An HVAC system, even if it's a pretty wimpy one, a little small one, is going to create pressures of 250 to 500 pascals. So the pressure differences that an HVAC system can create are very large. And what that means as a practical matter in terms of preventing problems is we've got to make sure that the HVAC system doesn't leak air any more than the building enclosure leaks air. Because if it leaks air, that means we're transferring the pressures of the HVAC system to the exterior wall. And therefore we're going to either suck humid air in or we're going to blow humid air out because of the vast, relatively much higher, many orders of magnitude higher pressures that would carry the HVAC. So the key with both building enclosures and especially HVAC is we've got to be tight. Got to be tight ductwork. Got to be very tight. Make sure that the pressures don't escape to cause problems with creating pressures across the exterior wall.
So, Terry, I would like to ask you, this is a topic that's been brought up in the building science community for quite some time. There's a lot of heavy emphasis on vapor diffusion, but since we're talking about air leakage and enclosure, do you mind just touching base on, moisture transport via air leakage as opposed to diffusion?
Oh, sure. For most buildings, the diffusion issues are relatively uncommon and small compared to air transported water vapor. And it's just because you can move with a fairly small pressure, humid air, through the enclosure into different parts of the building. And that's aggravated by something like a return plenum that has a lot of air leaks to the outside. And you have the air handler actually powering it. With diffusion, generally the cases that I've had where things have gone wrong and diffusion was a big part of it, that has to do with unusually high dew points inside buildings in cold weather, or in air conditioning season, siding systems, cladding systems that can absorb a lot of rainwater, and when the sun hits them, the cladding warms up because of the sun hitting them after the rain, the stored water turns to vapor, and now we have a really very high vapor pressure driving water through the wall into the building. Those are the cases where diffusion becomes actually really important. So a research hospital that's humidified and under positive pressure in the wintertime, well, that would have air leakage as well as diffusion. Swimming pools and therapy spas, places where the indoor dew point is in the high 70s. Those are places where you discover closed cell foam is not a good enough vapor barrier. You actually need a separate vapor barrier for that, a roofing system in a swimming pool area. So that would be a diffusion issue. But those are limited to these unusually high dew point issues.
So what you're saying essentially is that you love working on projects up in Alaska that have swimming pools. Is that correct?
Yeah.
There was one point that was brought up in this that I'd like to kind of harp on. So I'd like to talk about some HVAC strategies that can be utilized to keep a building dry. And B, there was something that was brought up that talked about designing an air conditioning system that humidifies even when there's no need for even when there's no need for cooling. So let's go ahead and talk about a system like that. So what would that type of system entail, and how does that system operate in order to keep a building dry? So Lou, would you like to touch base on that?
Sure, be delighted to. I think that when you think about humidity control, two things are useful to keep in mind. One, and maybe most important in my view, is that you got to figure out where that water vapor is coming from. And in a commercial building, it's really simple. With the exception of the buildings that Terry mentioned, which are museums and swimming pools and hospitals, with the exception of those, pretty much all other commercial buildings, there's one place where you have to where you have to watch out for humidity, and that is the ventilation air. So the ventilation air is all important if you're going to control humidity in a commercial buildings. And if you take the water out of the incoming ventilation air, then you have solved the problem. And if you do not take the water vapor out of the incoming ventilation air, then you have a problem and you're going to have difficulty solving it. It's going to be more expensive, it's going to be more difficult to do, and it will be less reliable. So if you care about humidity control in commercial buildings, just keep that one thing in mind, is dry the ventilation air all the time. The second thing that I'd like to point out, and Terry can probably provide examples of some of these problems, is that a lot of the difficulty that we see with respect to humidity control in buildings comes when the building is unoccupied. And if the building is unoccupied, we want to make sure we don't bring any ventilation air in, because that's, again, we're bringing water vapor into the building. So we don't want to do that. So think about what you do with an HVAC system when the building is unoccupied. If the building's unoccupied, don't really care too much about temperature as long as it doesn't freeze, But what you do still care about is making sure that the indoor dew point doesn't get so high that things condense when you start to cool it again. So when you're designing an HVAC system, it's a useful strategy, as you alluded to earlier, to have a separate unit that dries things out when you don't care about the temperature and all you care about is the dew point. And that's the case when you have unoccupied buildings. So two things. One is ventilation air, keep it dry all the time, and shut it off when people aren't in there so that you don't have that problem. And the second is have some system, some component, some set of controls so that you can keep the darn place dry if nobody's in there.
Alrighty, so we're going to kind of switch gears here a little bit. Very, very simple test that you guys bring up in the document. You referred to it a bunch, the pen test. This is critical. I've heard this test brought up in terms of thermal insulation and making sure there's a continuous barrier. So specifically, you guys, you do touch base on that, but you really are addressing the pen test for moisture-related control. Terry, would you like to discuss what that pen test is and how it's best utilized by professionals?
The idea is pretty simple. You should be able to trace a continuous layer of rainwater protection around the section of a building. It's from the middle of the roof all the way around down through the walls and the window systems to the grade and below grade and to the middle of the floor. The same is true for the air barrier. You should be able to take your pen and trace an air barrier continuously from the middle of the roof down to around the section to the middle of the floor. You can't really do that with vapor barriers. unless you're so far north that you don't have any cooling season, or so far south that you don't have any heating season. If you're in a place where you have to heat and cool, then condensation is a function of both the temperature and the vapor transmission. And so you have to evaluate the entire assembly rather than have the condensation control be in a single layer.
Great. So I'll go ahead and just ask you generally. So the layout of this document has multiple strategies that designers can put into place, but more importantly, ways that once constructed, you can actually test and verify that the strategies that you put forth in the guidance of this document have been achieved. Feel free to dive deep into this if you'd like. What are some of the detailed strategies that you are putting forth for designers, and what are some of the ways you can actually test and verify this stuff in the field?
So, for example, in wall sections, we are recommending that people use rain screen walls, that it's a drained wall system. That would be a strategy for achieving the goal of keeping rainwater out of the wall assembly. And to verify that, there would be written into the design documents and then actually conducted during construction a set of inspections that would inspect the substrates and the drainage clay materials that were being applied to the substrates. And there may be functional testing that goes along with that, like a pull test. So you have a sort of a little stand with a threaded rod, and the threaded rod will attach to a piece of plywood that's glued with quick-setting epoxy to the surface of, say, a peel and stick membrane. And you cut a circle around the piece of plywood, you let it set up, and then you have a gauge on it so that it can tell how many pounds of force it takes to pull the membrane off the substrate. It needs to be spelled out in the specifications. So It's something that the design team has to write everything they want the contractor to do, and the QA program that they want needs to be written in there. So that's one way in which it can be done. And for the rainwater control part, you could have an ASTM 1105 spray test to spray the windows and see if to determine whether they're installed effectively or not. And for the whole building air tightness, you could conduct a whole building blower door test. There are standards. The Army Corps of Engineers has a standard for conducting the test and a target. We don't have an air tightness target listed in the EPA guidance, but we do use the Army Corps of Engineers air tightness target as an example. We require having a target, but we don't tell people what it should be. That's what it comes down to.
Great. So that kind of talks about some of the verification and testing on the enclosure and some of the materials that would be put into place. Lou, how about some of the commissioning that would be involved? Do you guys give any guidance in regards to HVAC equipment there?
Well, we do, but it basically has to do with the idea that you test the air tightness of the airside system. And if you got a lot of leaks, that's a bad thing. And if you have none, that's a really good thing. And this is very much akin to the type of, actually, if I can sort of have a plug for what's been happening on the residential side with Energy Star, the whole idea of testing the air tightness of buildings and the air tightness of HVAC systems is really more developed on the residential side than it is on the commercial side. Terry and another group of building scientists has been pioneering the techniques necessary to test a really large building and really large air systems, and some of that is certainly in the book. But the residential side is actually more advanced. Home performance contractors do a pretty good job of measuring that stuff. But I think one of the things that I'd like to focus on about the guide as a whole, one of the things that I like about the book is that it gives a pretty good hierarchy of concern. And if you think about the problems of moisture in buildings, the way Terry and other folks have laid this out, you really want to think first about water leakage. You don't want water getting into the building, number one. Number two, when it gets in anyway, in spite of all your best efforts, you want it to get back out. You don't want it to stay in the building and accumulate. And in terms of hierarchy of concern, that's the first thing to think about that's really two things. It's really rainwater that hits the side of the building and rolls down, or it's water that comes from the roof and ends up at the foundation. So those places to focus for folks that are interested in moisture problems in buildings, focus right there first, and then after that, focus on making sure humid air doesn't get into the building, and that's an air barrier. So a tight building is a good thing because it prevents humid air from getting in, and a tight building is a good thing because it prevents water from getting into the building. But if water gets into the building, make sure that it can get back out so that it doesn't stay in the building and cause a problem. This does represent the best practices of building science as it's developed in the last 9 or 10 years.
Great. So that is your cue to download this document and put it into place. This document is free to download at epa.gov/IAQ/moisture. It'll also be linked directly to where you can download this podcast. And again, this is the Moisture Control Guidance for Building Design, Construction, Maintenance. Terry Brennan, Lou Harriman, thank you so much for talking with us.
Thank you very much, John.
Thanks, John.
This is John Bergman at Green Dream Group in Chicago.